Testing. Testing 1, 2, 3. Hello and welcome. Welcome back. So before we start, I think it would be good if we can go through what we have learned yesterday. So maybe let me start from the common programming concepts. Just quickly go through. Right, so there are keywords, and we have variables and mutability, immutable, mutable, variables gonna change, has to be mutable. And we can also create constants. It looks like this. You use the const keyword. And there is this concept also of shadowing, where here you declare a variable, so it's immutable. And you can use it again over here. But you need to use the let keywords. And this one is another scope where you can use X again here. differences between mutable and shadowing. So this one is not allowed. Yesterday we've gone through the data types as well. So this is a data type. So it can be both unsigned and signed, I for signed, which is for integer types. If you want to make it unsigned, use U. And you can also do some other number literals. And for clarity, you can put underscore between the numbers. There's this concept of integer overflow. So automatically it will wrap around. Floating point types. So you use F or prefix it with an F. We also have Boolean type. So you just need to take note that this is in a small letter. And instead of Boolean, you use bool. And then you also have this character type, CHAR, car. And you can also put in some emojis. Then you have these compound types. You can create a tuple. So a tuple can have different data types within them. So to access the value of the tuple, you can do it like this. Or you can have this dot notation, or using a period, where the number would represent the index. So it always starts from index 0. Then you can also create arrays. And within the array, you can define the data type and then the size. And you can also initialize it with some values. And to access array elements, array index starts from 0, like this, enclosed in square brackets. And when using arrays, of course, there's a tendency to have an overflow. Next concept was functions, where you had fn to define a function. So you can add functions anywhere within your code because this is compiled. It's not interpreted. You can also pass in parameters within the function, like x, and you define the data type. The difference between statements and expression: statements do not return a value, while expressions evaluate to a resultant value. So this is a statement. So you cannot do something like this because it doesn't return any value. This, however, will return a value. So this is allowed. It's within the scope. So whatever the values that it's in here, it will be binded to y. How to create functions that return values. There is this dash greater than sign. This is the data type. Comments. Okay, so comments in Rust is using slash slash. Then of course, control flow, you have if expressions. If, then condition, to close it in curly braces. Then you can also add in else statements. You can also do else if. You can also do inline if statements. If condition, if true, return 5. If condition is false, it will return 6. And then you have loops as well. So loop keyword. So this will this one will be an endless loop, not unless if you terminate it. Returning values from loops. So you can create a loop, define a scope, and then you can return a result. So in this case, it's counter. Sure if we covered this part yesterday, but let me go through these things. Loop labels. So you can also create loop labels. You have break and continue. So over here, you have a loop. If remaining equals to 9, break. If count equals to 2, break, counting up. This is counting up. With a single quote. So where is counting up? Oh, counting up is here. So it's like a label. counting up is a label. It will count up from 0 to 2. So initial value of count is 0. Then count here will increment, and when it becomes 2, it will break and come back to counting up. Exit the outer loop. Okay. So it will come out from this one to print. So it will end. Let's try this one out. Control flow. Songs. Let's use Visual Studio Code. Errors. Let's run it. Remaining 9. Remaining 10. Remaining 9. Count equals to 1. 9. So loop body is terminated. This loop terminated. Came back here. So remaining is again 10 to 9. So it terminates at this point and came back here. Count is now, initially count was incremented. And now count is 2, meaning it's still 10 because it gets reset here. It resets to 10 every time. But count doesn't change. It was incremented to 2. So it goes in. Still 10. And then count equals to 2. Break. It went up to here. Conditional loops with while. Will often need to evaluate a condition in the loop. The condition is true. Okay, this is true, so the condition is here. Okay, also the program calls break. Okay, so when the condition is true, it will call a break, thus stopping the loop. So you can also implement behavior like using a combination of loop, if, else, and break. We use while to loop the program 3 times, counting down each time, and then after the loop, prints a message and exit. Okay. So what we need to do here, maybe we can run from here directly. So it started with 3. It checks numbers not equal to 0. 3 not equal to 0. It will print 3. Number. Okay, so it so it decrements number, becomes 2. from 2 not equal to 0, prints 2, 1, then finally lift off. If it's 1, minus 1 becomes 0, so this statement becomes false. Then it jumps out and prints lift off. Okay. This construct eliminates a lot of nesting that will be necessary if you use loop, if, else, and break. It's suggesting that while is better than combining loop and if else statements. Okay, so here's one example. Looping through a collection with 4. So you have an array, mutable index equals to 0. Mutable, so it means index, the value can change. So while index is less than 5, print line, the value is A. A is the array. Index. So index starts with 0. Index is decremented. So while it's less than 5, it will print. So 0, 1, 2, 3, 4. Okay. Then it prints 10, 20, 30, 40, 50. Okay, let's try to run this one. Yeah. So here there's another type of loop you can use. For loop. We have an array. In this case, it did not use any variable here, like an index, but there's an element here. So element is what? Here we have an array. Okay. So most rustations would use a for loop. The way to do that would be to use a range. Okay, I missed this part. The safety and conciseness of for loops make them the most commonly used loop construct in Rust. Even in situations in which you want to run something a certain number of times, as in the countdown example that just one. The way to do that would be to use a range provided by the standard library, which generates all numbers in sequence starting from one number and ending. Here's what the countdown would look like using a for loop. Okay, so here number in 1 dot 4. So I think this is 1 to 4 dot rev. What is this dot rev? Rev is to reverse. Okay. Let's see. So 1 to 4. It's 1 to 4, but why do we have 3 to 1? Let's try this. Visual code. It's 3 to 1. versus an iterator's direction. Usually iterators iterate from left to right. If you're using rev, an iterator will instead iterate from right to left. Okay. So it will do a reverse. However, the range 1 to 4. Let's say that it did not print 4. Or you can also do it like this, 0 to 5. You can change the code a little bit. So if I put 5 here, 5, it should include 4. If I put 0 here, so it included the starting range, but it excluded the end range. So if you want to display from 1 to 10, you have to do something like 1 to 11. Yeah, so 10 to 1. If you remove ref, it should proceed in ascending order. Oh, we need to remove the parentheses. Okay, necessary. Let's remove the parentheses. Right? Yeah, so you got 1 to 10. So we only need to put in the parentheses if we want to use it within a function. So let's see what other options do we have. Compare, count, cycle contains. Because it's an iterator. Is rev here. Rev. So this is 10, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. Let's go back to this one. So in summary, learn about variables, scalar and compound data types, functions, comments, if expressions, and loops. Practice with the concepts discussed in this chapter. Try building a program to do the following. Convert temperatures between Fahrenheit and Celsius. Generate the nth Fibonacci number. In the lyrics, Christmas Carol. 12 Days of Christmas. Taking advantage of repetition in the song. Yeah, maybe we can do this some other time. Yeah, but for today's session, so it's a recap and a continuation from the other day, and then we move on to understanding ownership. Start understanding ownership. Ownership is Rust's most unique feature and has a deep implications for the rest of the language. I think this is the main foundation that you need to understand in Rust. It enables Rust to make memory safe, the guarantees without needing a garbage collector. So it's important to understand how ownership works. This chapter will talk about ownership as well as several related features, borrowing, slices, and how Rust lays data out in memory. What is ownership? Set of rules that govern how a Rust program manages memory. All programs have to manage the way they use computer's memory while running. Some languages have garbage collection that regularly looks for no longer used memory as the program runs. In other languages, the programmer must explicitly allocate and free the memory. Rust uses a third approach. Memory is managed through a system of ownership with a set of rules that the compiler checks. If any of the rules are violated, the program won't compile. None of the features of ownership will slow down your program while it's running. Okay. Because ownership is a new concept for many programmers, it does take some time to get used to. The good news is that the more experienced you become with Rust, the rules of ownership system, the easier you'll find it to naturally develop code that is safe and efficient. When you understand ownership, you'll have a solid foundation for understanding the features that makes Rust unique. In this chapter, you learn ownership by working through some examples that focus on very common data structure strings. Some more concepts. The stack and heap. Many programming languages don't require you to think about the stack and the heap very often. But in systems programming language like Rust, whether a value is on the stack or the heap affects how the language behaves and why you have to make certain decisions. Parts of ownership will be described in relation to the stack and the heap later in this chapter, so here's a brief explanation in preparation. Both the stack and the heap are parts of memory available to your code to use at runtime, but they are structured in different ways. The stack stores values in the order it gets them and removes the values in the opposite order. That's for the stack. This is referred to as last in, first out. Yeah, I think that this one is LIFO. Last in, first out. Think of a stack of plates. When you add more plates, you put them on top of the pile, and when you need a plate, you take one off the top. Adding or removing plates from the middle or bottom wouldn't work as well. Adding data is called pushing into the stack, and removing data is called popping off the stack. All data stored on the stack must have a known, fixed size. Data with an unknown size at compile time or a size that might change must be stored on the heap. Okay, so that's the main difference, what goes into stack and what goes into the heap. So if it's a known fixed size, it goes into the stack. If it's a known size at compile time, then it's stored on the heap. Heap is less organized. When you put data, okay, so this is the other difference between stack and heap. So in stack, you go with the last in, first out approach. For heap, it's less organized. When you put data on the heap, you request a certain amount of space. The memory allocator finds an empty spot in the heap that is big enough, marks it as being in use, and returns a pointer, which is the address of that location. This process is called allocating on the heap and is sometimes abbreviated as just allocating. So that's the term, allocating. Pushing values into the stack is not considered allocating. Another difference. Because a pointer to the heap is a known fixed size, you can store the pointer on the stack. But when you want the actual data, you must follow the pointer. Think of being seated at a restaurant. When you enter, you state the number of people in your group, okay? And the host finds an empty table that fits everyone and leads you there. If someone in your group comes late, they can ask where you've been seated to find you. So this is a very good analogy. So if we come back to the previous statements, heap, how do we do allocating? So there's this memory allocator. So I think that would be the one that guides you. Yeah, the one that will lead you. Finds an empty spot. So it finds an empty table in the restaurant and marks it as being in use and returns a pointer. So maybe the waiter will tell you, okay, your table number is table 5, table 8. So that's going to be the pointer. Okay. Pushing to the stack is faster than allocating on the heap because the allocator never has to search for a place to store new data. That location is always at the top of the stack. Okay, so because it does the last in, first out. Comparatively, allocating space on the heap requires more work because the allocator must first find a big enough space to hold the data. And then perform booking to prepare for the next allocation. Accessing data in the heap is slower than accessing data on the stack, so you have to follow a pointer to get there. Contemporary processors are faster if they jump around less in memory. Continuing the analogy, consider a server at a restaurant taking orders from many tables. It's most efficient to get all the orders at one table before moving to the next table. Taking an order from table A, then an order from table B, then one from A again, and then one from B again. Much slower process. By the same token, a processor can do its job better if it works on data that's close to other data, as it is on the stack, rather than farther away, as it can be on the heap. Makes sense. When your code calls a function, the values passed on into the function, including potentially pointers to data on the heap, and the function's local variables get pushed onto that stack when the function is over. Those values get popped off the stack. So this is in the case of a function. is very important. Yeah, let's read through again. When your code calls a function, the values passed into the function being potentially and the function's local variables get pushed onto the stack. When the function is over, those values get off the stack. So I think it has that concept of the scope. So at the time when you use it, it's within the stack, and when the function is over, it gets popped off the stack. Keeping track of what parts of code are using what data on the heap, minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so you don't run out of space are all problems that ownership addresses. Once you understand ownership, you won't need to think about the stack and the heap very often. But knowing that the main purpose of ownership is to manage heap data can help explain why it works the way it does. Ownership rules. First, let's take a look at the ownership rules. Keep these rules in mind as we work through the examples. Each value in Rust has an owner. There can only be one owner at a time. When the owner gets out of scope, the value will be dropped. Okay, so value has an owner, only one owner at a time. When it goes out of scope, the value will be dropped. Variable scope. Now that we are past basic Rust syntax, we won't include all the fmin code in examples so you're following along. Make sure you put the following examples inside the main function manually. As a result, our examples will be a bit more concise, letting us focus on the actual details rather than boilerplate code. As a first example of ownership, we'll look at the scope of some variables. Scope is the range within the program for which an item is valued. Take the following variable. Okay, maybe we should prepare the boilerplate code first so that we can also execute this within Visual Studio Code, because I don't think this one will run. Oh, it will run, but there's no output. This one, however, will not run. Oh, it will run as well. There's no output. It says, oh, okay, well, but anyway, yeah, let's try to create a boilerplate code. So here, how can we do that? Use cargo for that. Cargo new, maybe ownership. So to create a project ownership. City ownership. Let's check the structure. So we have cargo, the Toma, and me. Okay, so it's the low route. Cargo, low route. And then let's open this from Visual Code. Ownership. At this level, click open. Wrong, by mistake. Let's do it again. It should be ownership then open. Okay, we have cargo.toml here, and then we have me. Okay. So let's get back to this. Let s hello world. It's just hello. Static this? Static str. So it's not used. Here is just not s equals hello. Ah, it will generate a warning because it's not used anywhere in the code. Okay, so we can get rid of that warning by just print line. Yes, semicolon. What's this? Ownership. Okay, let's continue. The variable s refers to a string literal, where the value of the string is hard-coded into the text of our program. The variable is valid from the point at which it's declared until the end of the current scope. So within this one. Over here, s is not valid here, it's not yet declared. Here, s is valid. To stop with s, so we printed it earlier. This scope is now over and s is no longer valid. We can try that one out. Let's see. Maybe can we do something like this? Still define the scope and do a print line again here. Oh, seems to work. Yes, here. Let's terminate with semicolon. Let's see what happens. Oh, hello is still printed out. I thought it's already out of scope. S comes into scope is valid. It remains valid until it goes out of scope. At this point, the relationship between the scopes and the variable is valid is similar to that in other programming languages. Now we'll build on top of this understanding by introducing the string type. I didn't get it. Maybe my assumption is wrong. It seems to print hello still here. Okay, let's ignore that for now. The string type. To illustrate the rules of ownership, we need a data type that is more complex than those we covered in the data types section. The types covered previously are of known size, can be stored on the stack and pop off the stack when their scope is over, and can be quickly and trivially copied to make new dependent instance. Another part of the code needs to use the same value in a different scope. But we want to look at data that is stored on the heap and explore how Rust knows when to clean up the data. And the string type is a great example. We concentrate on the parts of the string that relate to ownership. These aspects also apply to other complex data types, whether they are provided by the standard library or created by you. We'll discuss string in more depth in chapter 8. Chapter 8, Common Connections. We've already seen string literals when a string value is hard-coded into our program. String literals are convenient, but they aren't suitable for every situation in which we may want to use text. One reason is that they're immutable. Another is that not every string value can be known when you, for example, what if we want to take user input and store it? For these situations, Rust has a second string type string. If we want to take user input and store it, so you use string. This type manages data located in the heap and as such is able to store an amount of text that is unknown to us at compile time. You can use string from string literal using the from function, like so. Okay, so yeah, this is a string literal. Maybe that's why printed it out within this parenthesis. Still works. But s equal to world is not allowed. Yeah, because it's immutable. And what we've learned the other day is we can do shadowing. So you can put let s here, and within this scope it should be world instead. Yeah, right. So I missed that point because s here is s is in the stack. No, s is what's the type of the data type? What's that data type? Statically typed language. Data type. Scalar type. Yeah, scalar type. But string here is different. So apparently, string can be created from a string literal. Okay. And it will be binded to s. So the colon operator allows us to namespace this particular from function. Okay, so from is a function from string. No, from string. So string is like a class colon from, and then you put in the value for the parameter. We'll discuss this syntax more in method syntax. Okay, method syntax. Where's that? Next chapter. And when we talk about namespacing with modules in paths for referring to an item in the module 3, which is in chapter 7. This kind of string can be mutated. Okay, let's copy this. Here. So okay, so s is mutable, and push str appends a literal to a string. Appends. So it's like concatenating. Hello, comma world. This will print hello world. So here we cannot run it. Oh, we can also run it. The code is incomplete. Yeah, of course it should show hello world. So what's the difference here? Why can string be mutated but literals cannot? The difference is in how these two types deal with memory and allocation. In the case of a string literal, we know the contents compile time. So the text is hard-coded directly into the final executable. This is why string literals are fast and efficient. But these properties only come from the string literal's immutability. Unfortunately, we cannot put a blob of memory into the binary. For each piece of text, the size is unknown at compile time, and the size might change on the program. With a string type, in order to support a mutable, growable piece of text, we need to allocate an amount of memory on the heap. So for string, it goes into the heap, which is unknown at compile time to hold the contents. This means the memory must be requested from the memory allocator at runtime. We need a way of returning this memory to the allocator when we're done with our string. That first part is done by us. Okay. And we call string from. Okay, this part here. Its implementation requests the memory it needs. That is pretty much universal in programming languages. However, the second part is different. In languages with garbage collector, GC, keeps track of and cleans up memory that isn't being used anymore, and we don't need to think about it. In most languages without garbage collector, it's our responsibility to identify when memory is no longer being used and to call code to explicitly free it, just as we did to request it. Doing this correctly has historically been a difficult programming problem. If we forgot, we waste memory. If we do it too early, we'll have an invalid variable. If you do it twice, that's a bug too. You need to pair exactly one allocate with exactly one free. Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of scope. Here's a version of our scope example from using string instead of a string literal. Okay, S is valid from this point forward. This scope is now over and S is no longer valid. Okay, outside this one. There is a natural point at which we can return the memory our string needs to the allocator. When S goes out of scope, okay, so the allocator return the memory of our string when S goes out of scope. When a variable goes out of scope, Rust calls a special functions for us. This function is called drop, and it's where the author of string can put the code to return the memory. Rust calls drop automatically at the closing curly bracket. Mhm. Note in C++'s pattern of deallocating resources at the end of an item's lifetime is sometimes called resource acquisition initialization, RAII. The drop function in Rust will be familiar to you if you use RAII patterns. Can we execute drop? How do we do that? Execute the destructor of this type. Drop and then the mutable. This method is called implicitly when the value goes out of scope and cannot call it explicitly also. This is a compile error. However, the memDrop function in the prelude can be used to call the arguments drop implementation. And this method has been called, itself has not yet been allocated. It only happens after the method is over. If this wasn't the case, self would be a dangling reference. Yeah. Okay, so I don't understand this one yet, but it seems like it cannot be called explicitly. Okay, let's continue. The pattern has profound impact on the way Rust code is written. It may seem simple now, but the behavior of code can be unexpected in more complicated situations. When we want to have multiple variables use the data we've allocated on the heap. Let's explore some of the situations now. Variables and data interacting with move. Multiple variables can interact with the same data in different ways in Rust. Look at an example using an integer. Okay. X equals to 5. This is immutable. But then X, is it copied to Y? Y is also immutable. Assigning the integer value of variable X to Y. You can probably guess what this is doing. Bind the value 5 to X, then make a copy of the value in X and bind it to Y. So it's creating a copy. We now have two variables, X and Y, both equal to 5. This is indeed what is happening because integers are simple values with known fixed size, and though these two 5 values are pushed onto the stack. Now let's look at the string version. S1 string from hello, S2, okay, S1 is also copied to S2. Let's see. This looks very similar, so we might assume that the way it works would be the same. That is, the second line would make a copy. Oh, but this isn't quite what happens. It's not copying it. Okay. Look at figure 4-1. 4-1 to see what is happening to string under the covers. A string is made up of 3 parts known on the left. A pointer to the memory that holds the contents of the string, a length, and capacity. This group of data is stored on the stack. On the right is the memory on the heap that holds the contents. Okay, so this is in the stack, and this one is on the heap. The length, how much memory in bytes the contents of the string is currently using. That's the length number of bytes. Okay. The capacity is the total amount of memory in bytes as the string has received from the allocator. The difference between length and capacity matters, but not in this context, so for now it's fine to ignore the capacity. So they look the same. Maybe in other objects, maybe this one will be different. When we assign S1 to S2, the string data is copied. String data. Meaning we copy the pointer, the length, and the capacity that are on the stack. So it's only copying, yeah. So it's only copying S2. Where is S2? S1, S2. So it's only copying the stack data. So it's also having the same pointer value. Okay, copy the pointer, the length, and the capacity that are on the stack. We do not copy the data on the heap that the pointer refers to. In other words, the data representation in memory looks like figure 4-2. So they're both hello, but there are two stack data, S1 and S2. The representation does not look like figure 4-3, which is what memory would look like if Rust instead copied the heap data as well. If Rust did this, the operation S2 equals to S1 could be very expensive in terms of runtime performance if the data on the heap were large. Yeah, so if the data the heap is large, it will consume the heap easily if you do this copy. It's like, if it's like copying it. Yeah, so it will be expensive, but that's not the case. Earlier we said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up the heap memory for that variable. But figure 4-2 shows both data pointers pointing to the same location. This is a problem. When S2 and S1 goes out of scope, they will both try to free the same memory. This is known as double free error and is one of the memory safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. To ensure memory safety, after the line let S2 equals S1, Rust considers S1 as no longer valid. Therefore, Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when you try to use S1 after S2 is created. It won't work. So after copying, you cannot use S1 anymore because it's already freed. Yeah, so this one will have an error. You'll get an error like this because Rust prevents you from using the invalidated reference. Let's copy this one. Borrow of moved value as well. So it will not run. If you've heard the terms shallow copy and deep copy while working with other languages. The concept of copying the pointer length and capacity without copying the data probably sounds like making a shallow copy. But because Rust also invalidates the first variable instead of being a shallow copy, it's known as a move. In this example, we would say that S1 was moved to S2. So what actually happens is shown in figure 4-4. Looks the same as here. With only S2 value. Okay, so it's a move. It's like a move function, or yeah, the term is move. It was moved to S2. Only S2 is valid. When it goes out of scope, it alone free the memory, and we're done. It means this one's moved here. In addition, there's a design choice that's implied by this. Rust will never automatically create a deep copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. This is another rule, implicit rule. So there's no such thing as deep copy. Scope and assignment. The inverse of this is true for the relationship between scoping ownership and memory being freed via the drop function as well. When you assign a completely new value to an existing variable, Rust will call drop and free the original value's memory immediately. Consider this code, for example. Okay, string from string literal to a mutable s, string from string literal ahoy to s. Since it's mutable, so the value can change. Then I think this one will print ahoy bird. Okay. We initially declare variable s and bind it to string with the value hello. Then we immediately create a new string with the value ahoy and assign it to s. At this point, nothing is referring to the original value in the heap at all. At this point, nothing is referring to the original value on the heap at all. Okay, because the original value is hello. And now it's pointing to ahoy. Okay. Then it means hello is already free. Representation in memory after the initial value has been replaced in its entirety. The original string thus immediately goes out of scope. Rust will run the drop function, and on its memory will be freed right away. When we print the value at the end, it will be ahoy. Okay. Variables and data interacting with the clone. If we do want to deeply copy the heap data of the string, not just stack data, we can use a common method called clone. Oh, so there's a way you can do deep copy using clone. We'll discuss method syntax in chapter 5, but because methods are a common feature in many programming languages, you've probably seen them before. Okay, so statics, string literal S1, and then S1 we're doing a clone into S2. S1 equals to S1, S2 equals to S2. So they're both hello. This works just fine and explicitly produce the behavior shown in 4-3 where the heap data does get copied. 4-3. Oh, this one. Okay, so it's cloning it. When you see a call to clone, you know that some arbitrary code is being executed and that the code may be expensive. It's a visual indicator that something different is going on. Stack only data copy. There's another wrinkle we haven't talked about. This code using integers, part of which was shown in listing 4-2, works and is valid. Okay. But the code seems to contradict what we've just learned. We don't have to call clone, but X is still valid and wasn't moved into Y. The reason is that types such as integers that have a known size at compile time are stored entirely on the stack. So copies of the actual values are quick to make. That means there's no reason we would want to prevent X from being valid after we create the variable Y. In other words, there's no difference between deep and shallow copying here. So calling clone wouldn't do anything different from the usual shallow copying, and we can leave it out. Rust has a special annotation called copy trait that we can place on types that are stored on the stack, as integers are. It's in chapter 10, generic types. Okay. If a type implements the copy trait, variables that use it do not move, but rather are trivially copied, making them still valid after assignment to another variable. Rust won't let us annotate a copy. Rust won't let us annotate a type with copy if the type or any of its parts has implemented the drop trait. If the type needs something special to happen when the value goes out of scope, and we add the copy annotation to that type, we get a compile time error. To learn about how to add copy annotation to your type, implement the trait C, derivable traits in appendix C. Okay, so we'll understand more about that in derivable traits. So what types implement the copy trait? You can check the documentation for a given type to be sure, but as a general rule, any group of simple scalar value can implement copy, just like integers. And nothing that requires allocation or some form of resource can implement copy. Here's some of the types that implement copy. Okay, integer types such as sign 32, Boolean, all the floating types such as F64, character type char, tuples, if they only contain types that also implement copy, for example. Okay. So if you mix string in between, then it cannot implement copy. Ownership and functions. The mechanics of passing a value to a function are similar to those when assigning a value to a variable. Passing a variable to a function will move or copy, just as assignment does. 4-3 has an example with some annotation showing where the variable goes into out of scope. Function main, You have string literal s, takes ownership s. Okay, so takes ownership s is another function here. And s values move into the function. So when s is passed here, it's being moved. And after the function is called, s is no longer valid. Okay, then here x equals to 5, makes copy, x is passed on to makes copy as a parameter. And because I32 implements a copy trait, x does not move into the function. So x is still valid here. And x goes out of scope, and s, because the s values was moved, nothing special happens. Okay, let's take a look at ownership. So s is passed here as some string. So s value moves into that function. Okay, so it will print hello. Some string goes out of scope and drop is called. Okay, the backing memory is freed. So that's why at this point s is no longer valid, because from within the function the memory is already free. While makes copy, this is I32. So x is copied here, and it prints this one. Some integer goes out of scope, nothing special happens. But since it's a copy, x will still have its value. Okay, let's copy it here. Some warning. Takes ownership is never used, but it's used here. Let's copy. Okay. Ah, so take here. Hello. So hello is displayed, fine. But if we modify the code and do a print, yes, borrow or move value as. So you cannot compile this one. Let's then implement the copy trait. Consider cloning the value if the performance cost is acceptable. Let's do a clone for now to get the quality. So No. Two, eight. Sorry. Try to use S after mm, if we try to use S after the call to takes ownership, Rust would throw a compile time error. These static checks protect us from mistakes. Try adding a code to main that uses S and X to see where you can use them, where the ownership rules prevent you from doing so. Okay. So X we already know that it makes a copy. Return values and scope. Returning a value can also transfer ownership. Okay, so here gives ownership. Gives ownership, return string. And here we have some string from a string literal. Some string is returned. So gives ownership at S1 will be yours. And then for S2, it's hello. S3 takes and gives back S2. So S2, hello is here. String comes into scope. And then hello, string is returned and moves out to the calling function. Moves out to the calling function. So it's in S3. S2 is moved into takes and gives back, which also moves its return value to S3. So I think S3 now is the owner. You cannot use S2 anymore. Takes and gives back. The string is returned and moves out to the calling function. Okay, let's see. The ownership of a variable follows the same pattern every time. Assigning a value to another variable moves it. When a variable that includes data on the heap moves out of scope, the value will be cleaned up by drop. Unless ownership of the data has been moved to another variable. While this works, taking ownership and then returning ownership with every function is a bit tedious. What if we want to let a function use a value, not take ownership? It's quite annoying that anything we pass in also needs to be passed back. If we want to use it again, in addition to any data resulting from the body of the function that we might want to return as well. Rust does let us return multiple values using tuple. Okay, going back to this statement where it's quite annoying that anything we pass in also needs to be passed back if we want to use it again. In addition to any data resulting from the body of the function that we might want to return as well. Okay, so there are instances where we want to retain the value of S2. Maybe we want to reuse S2 somewhere here, but we cannot do that. So we wanted to reuse S2 and use S3 somewhere here also. So shall we do? Maybe the next piece of code will give us the solution. Okay. Hello is in S1. Calculate the length. So S1 is passed here. Ideally, S1 will be already out of scope. And we cannot reuse S1 because calculate length takes ownership. But here S2 can be reused. And it also returns length. No, S2 is a different value. It's not S1. So what happens? S string. So S here is S1. And then it returns string and then unsigned integer with a size which could depend on architecture. So slen, S is being used, it returns the length of a string. The length here is unsigned integer. Then it returns S here and also length. So S is returned, it's being used as S2, also the length. It's using tuple. Okay. But this is too much ceremony and a lot of work for a concept that should be common. Luckily for us, Rust has a feature for using a value without transferring ownership on references. Okay. So it means we don't have to do this. There's another alternative here. References and borrowing. Okay, so maybe we can end here and let's do this on day 4 instead, because I think there's a lot of things to process here, mainly for the ownership. Okay, so let's do that in another day. In the meantime, thank you so much for watching. See you in the next video. Bye for now. Bye.